questions. So last time I had asked you guys, or we had finished sections 1, 2, and 3, and I asked you guys to start working on 1 through 22. Let's start with, in worksheet 1 as well, I guess. Start with any questions that we might have at this point. Oh boy, Zach.
Use number 20.
Sure. All right, so 20. The directions here say solve for the triangle if possible, so certainly there's possibility that there's like 0 triangles possible. So we definitely need to make sure that we're being careful when we're doing these. Okay, so I'm going to start by drawing myself a picture. So X, Y, Z. And then we'll add in my labels. So if I take a look, what situation are we in here? Side angle side, which is automatically a 1 triangle situation. So this is doable. We're just going to use the law of cosines, and it's just a 1 triangle situation. When solving a side angle side, the first thing we're going to do is find that missing side length. So using the law of cosines, I'll say z squared is equal to x squared plus y squared minus 2 times x times y times cosine z. And then to solve for z, I'll just square root both sides. Rather than copying that again, I'm just going to do a little edit-y there. And now it's calculator time. Just as a reminder, the mode that our calculator should be in should be degrees. Yeah, how did we know that? Yeah, the angles in the problem are in degrees. Very good. So I get 2602 for Z. Next up, I notice that I have angle Z and side Z, so I can use the law of sines to solve for one of the remaining 2 angles. But it does matter a little bit about which one of the 2 angles I want to solve for first, X or Y. What I want to make sure that I'm doing here is I didn't accidentally stumble into a side angle side situation that has like no triangles or 0, or 2 triangles or something like that. The way that I can guarantee avoiding that is, since I'm using the law of sines, to solve for the smaller of the 2 angles that are remaining first. So between X and Y, which one is the smaller of the 2? X. I can tell that because the side opposite angle X is smaller than the side opposite angle Y. Don't know why my OneNote just closed on me. Oh, it just decided to restart on me. That's equally as bizarre. So we cross multiply. Oops. and then divide by 2602. And then we'll do the sine inverse. So sine inverse of 13 times sine 102 divided by my previous answer gives me 2925. And then to get angle Y, I'll do 180 minus 102 minus 2925. And that should be 4875. And that's all she wrote. Does that feel okay, Zach?
Yeah, that makes sense.
So again, the place that it's easiest to make a mistake would have been trying to solve for angle Y instead of angle X at that point. And if you did that, it's possible you ran into something that caused you to get the wrong answer. Okay. So we just need to make sure that we're being careful when you're solving for angles, only when we're solving for angles. If you're using the law of sines and you have a choice between two angles, you want to find the smaller one. If you're using the law of cosines and you have the choice between angles, you want to find the bigger one.
That reminds me of something for the ones where it's two triangles that we have to solve, and one of the angles is supplementary. Is that always the bigger one on the?
It's so with the two triangles, you need to solve the second triangle in the same order that you solved the first triangle. So whatever the first angle you found in triangle 1, that's the supplementary one in triangle 2.
Okay. So
it has to be the same order. You're finding things in the same order that you did in triangle 1.
Okay.
Does that feel okay?
Yeah.
Okay. Grace. Sure. So 11 is a two triangles problem. So I'm not going to do any of the analysis here because we're told that there's two triangles. So there's, I don't have to worry about that. So I'm just going to start by drawing and labeling a picture. So I'll make a place to record my answers for triangle 1 and a place to record my answers for triangle 2. So I'm going to be looking for angle B, angle C, and then side C. To differentiate those between the two triangles, I'm going to add some subscripts so that I'm making sure that it's really clear where or which triangle the piece that I'm finding belongs to. And then I'm going to set up a space to do my work for each triangle. Now, the way I like to do this is I like to do triangle 1 all at once and then do triangle 2 all at once. You could go back and forth, hopping back and forth between them. But I think the odds of like getting some information confused and using the wrong stuff for the wrong triangle goes up by doing that. So I'm just gonna, every time I'm just gonna run straight through triangle 1 and then do triangle 2. Okay, so to set up triangle 1, I noticed that, hey, I have an angle on its opposite side. So I'm gonna set up my law of sines using sine 64 over side 16. And then I have an angle that I don't know, but a side I do, so that'll be the other half to my law of sines. I notice with angle C and side C, I know neither one of those two, so I can't do anything with that yet. So I have to start here with angle B. And really, I guess I should write this as B1. Okay, so I'll cross multiply. And then divide by the 16. And then to get rid of the sine, we do sine inverse. So that gives me 7274. Now getting angle C1 is really easy because I have 2 of the 3 angles. Grace, still doing good? Yeah, okay. I'm just checking in. I'll do that periodically. So that gives me 3926. And now that I know one of the 2 values for C, I can use the law of sines again. To solve for side C1. So we'll cross multiply. Yes.
I think when you did the subtract, you put a 68, not 64.
Oh,
I don't know.
did I goof it? Yep, sure did.
Sorry,
That's okay. So let's just do it this way. 64. Thank you for telling me before I get too far into this. There we go. 4326. Mistakes happen, right? I appreciate you paying attention and keeping me honest. The last thing we'd want to do is like get all the way through the whole thing and be like, hey, this thing was wrong. And it's like, oh, gallop and goblins, I got like 100 things now to change. All right. Okay, so this is rounding out triangle 1. And you'll notice that nothing unusual has happened in triangle 1. This has pretty much gone just to form like any other law of sines problem that we had done. So I get 1220 for C1, or side C1, I guess I could be specific here. So far, so good? Now, the trick here on triangle 2, the piece that maybe I didn't do a good enough job emphasizing last time, was the order in which we find the values in triangle 2 has to be the same order that we used in triangle 1. So the first thing I need to find is my angle B2, and then I'm going to find my angle C2, and then I'm going to find my side C2. Okay? So the relationship between the first angle you're finding in triangle 2 and the first angle you found in triangle 1 is that they're supplementary. Oops, too far. So that's 107.26. And now that I have that, I can solve for C, because once again, the 64, that given angle is part of both triangles. So I get 874 there. Doing so far so good, Grace? Okay. Notice here that triangle 2 is actually a little less work than triangle 1 was. Right? Triangle 1, we had to do the law of sines twice. In triangle 2, we only have to do the law of sines once to find this side C2. We're going to do it the same way, though, just using the law of sines and angle C, well, C2 in this case. So if I buzz through a little bit of the algebra here, I get that C2 is 16 sine of 8.74 divided by sine 64. Grace, are you good with me buzzing through that algebra there?
Yeah.
Okay. I figured at this point it's like the algebra is like the same over and over and over again. It's nothing really tricky going on. And it's the exact same, really exact same problem we just did a moment ago. So it just has like one number different somewhere. So I get 271, and that's my last piece I needed. Does that feel good? Of course, no problem. Jordan?
Can you do number 6 from worksheet?
Sure.
Well, I know you already did it, but you did like side angle, side, not really side.
We can do it. It's not a big deal. Okay, so let's start by drawing our picture. So this is side angle side. So to do this, or side angle, excuse me. So we will be using the law of sines. In a side angle situation, the first thing we need to do is check the size of that given angle. In our case, that given angle is x. Is x acute, right, or obtuse? Acute. Okay. So acute angles are either going to make one triangle or it's going to have that ambiguous 0, 1, 2 situation. To decide which one of those two things is going on, we need to compare the side opposite our given angle, which in our case is x, with the other given side, which in this case is z. Is x smaller than z, equal to z, or bigger than z? X is smaller than z, right? If you can read my penmanship there. I guess that 3 isn't super duper clear. So that tells me we're in the ambiguous 0, 1, or 2 triangle situation. Okay, to sort out what's going on there, I'm going to do the longer side times sine of the given angle divided by the shorter side. And the value there, that number, is going to tell me how many triangles I got going on. Okay, so I got 0.905. Since that value is less than 1, I know I have two triangles. Bummer! It's the long situation. Okay, so let's go ahead and make a place to record our answers. Jordan, everything going okay so far? Okay. Again, if I do something you're not sure about or that you don't like, please stop me and say something. That goes for anybody else. Again, if I do something that it seems like I don't know why he's doing that, that seems wrong, please stop me so we don't go ahead and do like a whole problem with when Mr. Kulik's written down the wrong number or something and have to go back and like fix it all over again. You know what I mean? That's just a hassle for everybody. Okay. So again, I set up a place to record my answers, a place to do my work. Now I'm going to go ahead and start rocking and rolling here. So just like before, we're going to start with a law of sines. So I have angle x and side x. So sine of angle x over side x is going to equal sine of angle z1 over side z1. Jordan, are we okay shortcutting through some of these algebra steps?
Yeah, I'm good. I was just confused on what part. So you're.
Oh. Okay. Does anybody want me to finish this? If Jordan's seen what she needs from this, there's probably no reason to keep going on it unless somebody else is interested in seeing the finish on this, which I'm happy to do, but I don't want to just like do problems for you guys to watch me do problems if you're not really interested in me doing the problem. You know, totally fine if you're interested, but if you're not, like, let's save everybody some hassle and go on to the next question, you know what I mean? Okay, so next question it is. That's fine. Lexi?
Can we do number 5?
The same sheet? Oh, the problem set? Absolutely. Where am I even at on this sheet of paper here? Maybe I'll go back over here or something now. Okay, so here the directions just ask whether there's 0, 1, or 2 triangles possible. It doesn't actually ask us to solve anything, so this is just an analysis problem. So I'm just going to start by drawing and labeling a picture. Now, you'll notice that when I do this, every time I draw my picture, my triangle looks exactly the same, regardless of like what the angle measures are or whatever. I'm not making an art exhibition here. I acknowledge this is not even close to scale. Like the 130-degree angle I just wrote there is clearly looks acute. But like, I don't really care because all I'm trying to do is figure out like what scenario I'm in, right? Lexi, you're good? Okay. So if I take a look at this, we see that this is side-side angle. Okay, so this is the weird one. The first thing I need to worry about is the size of the angle that's given to me. And it would be angle A, which is 130 degrees, so that is obtuse. So in the obtuse or right triangle situation, we can only get 0 or 1 triangle. There's no 2 triangles possible. There's no ambiguous case possible. And all we need to do to check is we just need to look at the side opposite the given angle and make sure that's the biggest side. I notice here that it's not, right? So there's no triangles possible. If it was the biggest side, then one triangle is possible. And that's it. That's the gist of it. Even if this was a solving problem, we'd be done because there's no triangle possible. What am I solving here, right? Nothing. Lexi, does that feel good? Sure. So just to kind of re-summarize here in this SSA situation. So if the given angle is greater than or equal to 90 degrees, and the side opposite the given angle is the biggest, then we get one triangle. Otherwise, there's no triangles. And then if the given angle is acute and the side opposite the given angle is smallest, then that's the 0, 1, or 2 triangles. Otherwise, we just get one triangle. So that's the same thing as all those cases that we wrote out last time, and just written in a way that's a little bit easier or a little bit more practical to use. So I've condensed some things together because we saw that the right triangle and obtuse triangle are really the same case. We observed that last time, so just put that all together. And basically, if one thing happens, you get a different result. If the other thing happens, everything is the same. So I'm just going to write it as like, what's the one thing, and then the otherwise, So that's probably the more practical way of kind of memorizing that SSA case. It avoids all the like side AB greater than BC stuff that it's like, okay, well, if my pieces are named like PQR, now I have to worry about like relabeling everything and like making sure that all that crap matches up. And just, if I'm given something technical, the first thing I'd want to do is like summarize it in a way that's really practical for me to use, which I think this does a nice job of. Sure. So this is really the way I'm thinking about it when I'm doing these problems. Like, I know the other thing because I'm the math teacher and I've done this like a million times. But like, really, this is what I'm thinking in my head, which is much easier to remember than the alphabet soup that we had written down in the notes. Who's next? Tommy? Sure. So 18. This is a side situation. Which means that we should be using the law of cosines. But before we use the law of cosines, we need to do a check here, because the side is one of those that different things can happen. Really only two different things can happen. Either you get a triangle or you don't. Does everybody remember the check in the side situation, Aiden?
You have to make sure that the two smaller sides added up are longer than the hypotenuse.
Yeah, the sum of the two legs has to be greater than the hypotenuse. So again, the hypotenuse is just the longest side, not necessarily the third side listed, right? Can you count on Mr. Kulik being a sneaky jerk and like making sure the hypotenuse isn't necessarily the last side listed? You betcha. That sounds like an excellent thing Mr. Kulik will do to just make sure you're paying attention. But it makes me less of a sneaky jerk if I'm warning you that I'm going to do that. Now I'm just sneaky, not necessarily a jerk. But clearly here 13 plus 16 is greater than 25, so we have a triangle. So we're going to use the law of cosines to solve for one of these angles. Since I have all three sides, I could clearly have enough information to solve for all three angles. The problem with that is, depending on what you solve, you may end up stumbling yourself into an SSA case with 0, 1, or 2 triangles later on, which is kind of a nightmare because, one, you have to recognize that that's what's going on, and then two, probably the information you want is in the second triangle and not the first triangle, and it's like, how do I even tell which information I want? It becomes like this whole thing that it's easier just to avoid. The way to make sure you avoid it is that when we use the law of cosines and we have the choice between multiple angles to solve for, we're always going to try to find the biggest angle. In this case, that's obviously which one? O. Why do I know O is the biggest angle? It's opposite the biggest side. So I have O squared is equal to m squared plus n squared minus 2 times m times n times cosine of O, well, angle O. So to solve for angle O, I'm going to just start by subtracting the 13 squared from both sides and then the 16 squared from both sides. I can't add the 2 times 13 times 16 to both sides, though, because that's being multiplied to my variable. So to move that stuff over, I have to divide it, since it's being multiplied to my variable. And then to get rid of the cosine, we do the cosine inverse to both sides. And then it's calculator time. I want to warn you guys or caution you guys about dropping that negative sign. Very easy to do that. And it'll really do a number on getting the right answer if you do that. I said do. I always have to laugh when I do that. There's no reason this can't be fun, guys, right? Or at least as fun as we can make it. If you can't laugh at yourself, I don't know what you're supposed to laugh at. Oops. And again, notice that I'm using the fraction command when using this or typing this into my calculator. This is a situation where you really want to make sure you do that, because to get the order of operations right, you need a whole boatload of parentheses. And it's a heck of a lot easier to just type it in the way it looks like on your sheet of paper than it is to mess with all that parentheses. So I get 118.74 for my angle O. Now, if I look, I know a side I know an angle and the side opposite it. So I could use the law of sines at this point, which I'd probably prefer to do because the formula in the algebra is a little bit simpler. Now, once again, I have a choice between two angles to solve for. I have enough information to solve for angle M or N. Again, I need to be careful because I don't want to run into an SSA case where I can get 0, 1, or 2 triangles. I want to avoid that like the plague. To make sure that I do that, I want to this time find the smaller of the two angles, which in this case would be which one, M or N? would be m. So again, the trick here is when solving for angles, and we have to only worry about it when solving for angles. If you're using the law of cosines and you have the choice between multiple angles, you want to find the biggest one. If you are solving for multiple angles with the law of sines, you'd want to find the smaller one. And again, I'm going to skip the algebra here. I hope that's okay. Is that good with you, Tom?
Yeah.
Okay. I figured it would be. I mean, it's all like the same algebra over and over and over again, right? It's one of those things like once you've done it a couple of times, it's like, yeah, I got it. Yeah, I got it. And just FYI, come like, on a test or a quiz or whatever, like if you show me the setup and you show me what you typed in your calculator, I'm good with that. You don't have to give me like a bunch of the intermediate stuff, But I would like at least those two pieces, like what you started with and what you typed in. And now I forgot what number I read here. 2713. And then now that I have two of the three angles, really easy to get that third one. So 3414. Cool? Okay. I'm cool too. Totally cool. Really cool. Yeah, definitely. All right. Anybody else on questions here? In general, most of this stuff is pretty straightforward. It's just a question of like doing some practice on it to make sure you've got all the details squared away in your head. But like the algebra steps are all quite easy. You know what I mean? As they're very repetitive. All right. So moving forward then, let's do the last section here. Okay. So let's say we're going to be talking about areas of triangles. So, okay, we have some generic triangle here with side lengths ABC and angle measures capital ABC. If you went back to geometry, how do we find the area for a triangle? What's our basic area formula for a triangle? Yeah. 1/2 base times height. So in our picture here, what's the base and what's the height? Yeah, Zach?
The base is B.
Okay. Oops. So if we pick B to be the base, what does the height then become? Lexi? Well, it's not necessarily split down the middle, but it's a perpendicular from B to from angle B to that side B, right? Do we know the length for capital H if what we have is a solved triangle? Nah, we don't, right? So this is kind of a hassle. I want to point out to you that there's nothing special about picking side B to be the base. We could have picked, say, side C to be the base, in which case then, like there's our height. Or you could have picked side A to be the height, or the base, in which case there's like the height. You guys kind of remember this from geometry? Okay. So the hassle here is, if what we have is a solved triangle, we don't necessarily have the height, right? Now, in one case, we will. What's the one case where a solved right triangle also would give us the height? If it's a right triangle, yeah. Yep. Because then just the legs are the base and the height. So let's say we go back to this scenario. And let's say we've picked B to be the base. And we're using this height here. I notice that I have a right triangle there in yellow. Everybody agree with that? So since it's a right triangle, I can use SOHCAHTOA, and I can say that sine of angle A is equal to opposite over hypotenuse. And to get the h by itself, then, I can multiply both sides by side C. So my 1/2 base times height becomes 1/2 side B times side C times angle A. There's a formula for the area of a triangle that I can solve for with any solved triangle, right? Because now it's only relying on side lengths and angle measures. Those are things that we have. Just real quick here, specifically, the best case scenario, if I have side B or side C, side B, and angle A are what I need. What's the best case scenario for this? If I have a side angle side situation, because then there I don't really need to solve the triangle at all to get the pieces I need to plug into the formula, right? If I had like an angle side angle, I'd have to solve enough of the triangle so that I get a side angle side situation that I can plug the formula into, which is a hassle, but like not something we haven't done before, you know. Everybody feel okay here? Okay. There is an alternate version of this formula that's called Heron's formula that says area is equal to the square root of S times S minus A times S minus B times S minus C, where S is the quantity A plus B plus C, all divided by 2. Sometimes we call this number S the semi-perimeter, because A plus B plus C is going to be the perimeter of our triangle. And if we're dividing by 2, it's like half, right? So like a semicircle is half a circle. This would be like a semi-perimeter. Yes, sir. Mm-hmm. Yeah. In what scenario would I want to use this Heron's formula? In a side-side-side situation. Very good. Since it's relying on just the values A, B, and C. That would probably be the only time. Yeah. Unless you've bothered to solve the entire triangle, because you'll run into the side angle side situation at least at the same time, yeah, before you've gotten to the side situation, because I think in every scenario, the last thing we're finding in our triangle is a side length. So, now, I said here at the beginning that Heron's formula is just a different version of the same thing. Let's see why, because boy, those two do not look alike if I'm looking at this, right? You guys agree with that, I would suspect. So this process that we're about to do is not something that I'd ever expect you to repeat, but I would expect that when we do this discussion, you're able to kind of follow the reasoning of what I'm doing. But this is a pretty long, strange trip here. So, all right, so we're going to start with our previous area formula. I'm going to multiply both sides by 4. Okay, sure, whatever you say, Mr. Kulik. I'm going to square both sides. We okay there? Now, I notice on the right-hand side, I have a sine squared c. If I think back to last semester, I have a trig identity for that situation, that sine squared is the same thing as 1 minus cosine squared. So I'm going to go ahead and make that substitution. And then I'm just going to go ahead and distribute that 4a squared b squared through. Everybody still so far so good? Now, if I look at that right-hand side, what I notice is that I have something squared minus something squared. You guys agree with that? It's really a difference of 2 squares. So I could factor this. But before I factor this, there's something else that sticks out to me. 2ab cosine c. Does that look familiar to you guys? That is part of our law of cosines, right? That if I add that 2ab cosine c to one side, and then subtract the c squared to the other side, I can make a substitution here. And I'm going to do that before I do that factoring. Is that okay? So I just made a substitution based on the stuff that I wrote there in red. Now I'm going to do my factoring. So that's going to be 2ab plus a squared plus b squared minus c squared times 2ab minus a squared plus b squared minus c squared. So I'm going to go ahead and just rearrange things a little bit inside these parentheses to point something out. So in the first parenthesis, since everything is positive, I'm just going to put the plus 2ab in between the a squared and the b squared. No big deal, right? All I did was just change the order I'm adding things. In the second set of parentheses, I'm going to move the 2ab inside of here, and I'm going to pull the c squared out. So that's going to be so the c squared is positive minus a squared minus 2ab plus b squared.
Why is the c squared plus?
Because to get it out of there, I had to distribute the negative through. Just like to put this thing in, I had to put a negative into it.
And wouldn't the negative be gone though afterwards?
No, because the negative still is applying to the a and the b that I haven't pushed through. If it's easier, you could distribute the negative through to everything and then refactor it all back out at the end. It's doing the same thing. I'm just trying to write down not every, you get it, right? All right. If you look at these two things, those should look familiar. Those are perfect squares. So I can factor those as well. So that's a plus b quantity squared minus c squared. And I have c squared minus a minus b squared. Everybody okay there? Take a look at each of those. What do you see? A difference of two squares. Again. So, okay, well, let's factor them again. So that's going to be a plus b plus c squared plus c, and then a plus b minus c, and then c minus, c plus a minus b times c minus a minus b. So I'm going to now just kind of drop the inner sets of parentheses here. And do a little bit of light rearranging. Okay. The next thing I'm going to do is inside this second set of parentheses, I'm going to add c and then subtract c, which is the same thing as doing nothing at all, right? And then in the third set, I'm going to add b and subtract b. And in the third one, I'm going to be adding a and then subtracting a. The reason I did that is if I look now inside each set of parentheses, I have an a plus b plus c. Everybody see that? If I go way back to my formula, a plus b plus c is equal to 2s. Right? If I multiplied both sides by 2, I could say that. So I'm going to go back in and make that substitution. We're getting real close now, guys. So I have 2s times 2s minus 2c times 2s minus 2b times 2s minus 2a. Cool? Okay, if I look inside of each of those parentheses, I see a greatest common factor of 2. So I'm going to factor that out of each of these. Oops. And since everything on the right-hand side is being multiplied together, I can multiply that in any order I want. So I'm going to put all those 2's together. 2 times 2 times 2 times 2 is 16. And then I'm just going to change the order there a little bit. If I divide both sides by 16, the 16s just cancel out of there. Oh my goodness, we're so close. And then I just square root both sides to get rid of the squared on the a. And there is my Heron's formula. Now, do I ever expect you to be able to repeat that yourselves? No way. Do I expect you to kind of be able to follow the algebra that I'm doing there with a little bit of light narrative on it? Yeah. Notice nothing in here we did that was outside of the skill set from either trig or algebra 2. Mostly what we were just doing was factoring, making a substitution. We used one trig identity. You know, we had to use the law of cosines to make a substitution. But overall, the tools that we used here were not things that were beyond you. Now, putting this all together to do what it was supposed to do would have been quite an ask. But to follow what somebody else has already done, I think is probably a reasonable ask. All right, let's do a couple of quick examples, numeric examples, and then get out of here. So again, we're going to start the same way by drawing and labeling our triangle. What situation are we in? Side angle side. So we'll just use that first area formula. So 1/2. The two given sides times sine of the included angle. And just calculator time at that point. Not much to do here. Are you kidding me, Mr. Kulik? That's so easy. Yeah. Is there any way it would be any harder? I mean, if you had to solve the triangle to get the pieces you needed, I guess, would be the only way I could make it any harder. So there's my area, 9207 millimeters squared. Mr. Kulik, I like it. I like it a lot. Okay, one more example here. Mm-hmm. Okay, and as Evan predicted, this is side, side, side. So I can just jump straight into Heron's formula, right? Nope. Nope. I need to make sure it's a triangle first, because side, side, side doesn't guarantee it's a triangle. Is Mr. Kulik a sneaky jerk and would give you something that, like, is not a triangle? Well, you better be prepared that I could do that. Again, I'm just sneaky if I tell you I might do it later. Not a jerk, right? All right. So there's that. So this is a triangle. So again, yes, let's start by finding the S. So that's 23/2. So my Heron's formula is going to be the square root of S times S minus A times S minus B times S minus C. And then it's just calculator time, my dudes. I'm going to take good advantage of the ANS function on my calculator, so I don't have to type in as much stuff. So I'm just going to do ANS times ants minus 5 times ants minus 8 times ants minus 10. So 1981. And I think the units there we gave were meters, so those would be square meters. No biggie, right? Area problem's pretty easy. Lot shorter comparison than the previous problems were anyways, that's for darn sure. So at this point, now that we've done section 4, you guys should be able to do the rest of 23 through 30. So that'll be part of Sunday's homework check as well. And that's it for today. What didn't we do today? Homework quiz. What should you count on for next time? Homework quiz. Aiden.
Since it's MLK on Monday, will you check the homework on Monday or will you wait until Tuesday?
I mean, realistically, I'm not doing anything on Monday. But I'm going to still say the homework due date is Sunday because, but yeah, I mean, I'm not checking anything till Tuesday morning. You and I both know this.
Yeah.
Lexi.
Is the homework quiz going to include this most recent section?
It would the homework quiz would be sections 1 through 3. So nothing that we did today.
Alright.